morning, this is Alaa Amir Sarhan, and today I'll be presenting my research titled Time-Stepping Meshless Transient Dynamic Analysis of Two-Dimensional Elastodynamics. We will start with an introduction, then go through the proposed formulation with its implementation, then numerical examples with the results, ending with a parametric study, and outlining recommendation and possible work extension. In this research, we focus on a very important topic in the field of engineering, which is dynamic analysis, specifically for two-dimensional problems to predict the behavior of mechanical and structural systems. One of the most popular methods for dynamic analysis is the boundary element method, which revealed very sufficient results either in the direct or indirect approaches. Boundary element method mostly requires boundary discretization only, which reduces computational efforts and simplifies modeling process. Several techniques used for dynamic analysis, such as time domain technique, boundary domain technique, the Dewey reciprocity technique, Laplace transform, harmonic analysis, and direct time differentiation. Each one of these techniques has its own advantages and disadvantages or limitations, such as, for example, for the DRM, the accuracy of results is highly dependent on the choice of the approximating radial basis function. As another example, the time domain technique requires domain discretization, which is a time-consuming procedure in addition to adding additional unknowns inside the domain. In some cases, domain integration appears due to the existence of certain domain load inertia terms or due to nonlinearity. Many researches have been done for the treatment of domain integration, either by transforming the domain integration to the bound using the DRM or discretizing the domain of the problem into cells. For this formulation, the main advantage is to develop a new totally meshless validated formulation for two-dimensional elastodynamics using method of fundamental solution combined with time differencing fundamental solution and treating the domain integral using Monte Carlo integration technique. Considering an arbitrary 2D body have a domain omega enclosed within a boundary gamma and subjected to in-plane dynamic loading as shown, starting from the governing differential equation in its strong form, Navier equation at a certain time t can be rewritten as follows in equation 1. Then expanding the acceleration at equation 1 by a suitable finite difference scheme. Here we choose Hobart scheme in equation number 2. Substituting from equation 2 into equation 1, the governing partial differential equation at certain time t can be rewritten as follows in equation number 3. Then equation number 3 could be rewritten as follows as a homogeneous part and non-homogeneous part as shown in equation number 4. And B term is a known generalized term consists of displacements of previous steps as shown in equation number 7. For this formulation, the displacement and traction could be decomposed into two solutions. The complementary solution, which represents the homogeneous part of equation number 4 with specific complementary boundary conditions, and the particular solution, which represents the non-homogeneous part of equation number 4 with no boundary conditions, as shown in equation 8 and 9. As shown in figure, the problem boundary gamma defined by boundary conditions embedded in an infinite domain. Also, it demonstrates an arbitrarily located in source point xi with intensities phi on another auxiliary boundary s, as shown in figure. For this for the particular part of solution of displacement and traction in equations 8 and 9 are computed using Monte Carlo integration technique, considering n field points, x points is the field points on the auxiliary boundary gamma, and R internal points inside the auxiliary boundary gamma as demonstrated in figure, where Monte Carlo technique has achieved a notable efficient result in integration for multidimensional problems due to its clarity and simplicity of application. The main idea of applying Monte Carlo technique for estimating this particular integral is to estimate the value of a certain function for a set of distributed points. Then find the average of the integral over the domain and multiply it by the area of the problem, as shown in equation number 10 and number 11. After computing the particular solution, complementary boundary condition is estimated as follows. Boundary condition complementary equals boundary conditions prescribed boundary conditions minus particular boundary condition, as shown in equation 12. Then the complementary solution of equation 8 and 9 are computed using the method of fundamental solution as a set of summation considering n discrete points as follows in equation 13 and 14. Since the b term in equation number 4 is always known at any time step, then the only unknown in the following equation is the 5 vectors, which are computed in a matrix form using the following equations, equation number 15 and 16, where U complementary and T complementary are complementary displacement and tractions calculated in equation number 12. After the solution of equation, the displacement and traction could be easily estimated by substituting into equation 8 and equation 9. Then the internal displacement is computed to be used for the next steps as follows in equation 17. Numerical implementation. This formulation is implemented into a Fortran code as shown in the following flowchart. After reading the required data from the input file, then we computing the coefficient matrix, A matrix, then initialize the time loop, updating the domain vector. Then after solving the system of equation and getting the 5 values, we can compute the boundary displacement and traction. Also, we can compute the internal displacement. To validate the efficiency and accuracy of this formulation, several numerical examples were solved, including tension, bending, and stress concentration problems. Results compared to previously published results and revealed very good agreement. Example number 1, cantilever under axial loading. Rectangular cantilever subjected to heavy side uniform load with the following material properties. This example is examined using 2 meshes. Mesh number 1 using 48 nodes, 8,192 internal points, offset 8 delta t times step size equal 0.0018 second. Mesh number 2 using 72 boundary nodes, 6,272 internal point, offset 8 times step size equal 0.0016. And this is the results of cantilever under axial loading compared to Domingos and reveal a good agreement. Example number 2, a rectangular cantilever subjected to flexural load time variant as shown with the following material properties is examined using 2 meshes and compared to previously published results from Dominguez and Farid and Rashid. This is the results of cantilever under flexural loading compared to boundary element, the results of Dominguez for boundary element and finite element methods. Example number 3, frame with lateral pressure with the following material properties is considered using 2 meshes as shown in table and compared to Brebi and Nardini. This is the results of the 2 meshes compared to results of Brebi and Nardini. Example number 4 is a stress concentration problem in which tensile specimen in axial tension as shown in figure. The material properties shown. This problem is considered using 2 meshes and compared to viscous results. This is the results of notched tensile specimen, results of 2 meshes compared to the DRM results. Parametric study. A study of each parameter's effect is conducted to investigate how these variables influence the results. These parameters are the number of boundary nodes, offset distance, number of Monte Carlo integration points, and time step size. Studying the impact of these variables is essential to ensure both the accuracy and stability of this formulation. This study is conducted using example number 1. This is the effect of number of nodes, different values of a different number of nodes on the results. This is the effect of different values of offset distance. This is the value of different meshes using different values of number of internal points. And this is effect of using different values of time step. To conclude, this formulation offers both the benefits of time differencing and simplicity of being a meshless. To examine the validity and efficiency of this formulation, several examples were solved. To strengthen the method even more, additional trials is required to determine suitable range of each variable. This work could be extended to three-dimensional elastodynamics. Thank you.